In a previous video, we've seen that if you reverse bias a PN junction and put a very high voltage across it, then it undergoes a breakdown. A very heavy current starts flowing, and that happens due to avalanche effect, where free electrons, when they're moving through, they start colliding with these bonded electrons, knock them off, creating more charge carriers. But in this video, we're going to see another mechanism in which a diode, a very heavily doped diode, undergoes breakdown. Such heavily doped diodes are called Zener diode because it was discovered, the effect was discovered by this man called Zener, and this breakdown phenomena is named as, no surprise, Zener breakdown. So let's get to the bottom of this whole Zener thing. If we go back to our conventional diode, a normal PN junction that we've been speaking about, then even without applying any voltage across it, you may recall that right at this junction, there is this depletion region over here. So there is a depletion region, a region which is depleted of charge carriers, and there's an electric field that exists over here, this way. And to see why that electric field exists, we'll have to zoom in a little bit. So let's zoom in over there and see what we get. So if we take a small section of that, and if we zoom in, then we'll find in the depletion region over here, we have these positive p ions and we have these negative boron ions. And it's because of this, you can see they're charged particles, and the charged particles end up creating an electric field. So that's really causing that electric field over here, right? And this now is the current width of the depletion region. Now, if you have, say, a very heavily doped diode, so let's bring in a very heavily doped diode. So we can imagine this is pretty much the same as this. It also is silicon, and you have put the same impurity, but the only difference now is that you have more doping, which means there are more impurity atoms, more impurity ions per centimeter cube. Then what we'll find, the difference over here would be its depletion region. If you write down its depletion region, that would be extremely narrow. The depletion region would be very, very narrow. And the reason for that is because the field over here turns out to be extremely strong. So the electric field, again, we have not applied any voltage, but the inbuilt electric field over here turns out to be super, super strong. And again, to see why, let's zoom in over here. If we zoom in, we'll find this now. What we will see is because there are so many dopant, there are so many impurities, you'll find more number of more number of these ions per centimeter cube. And now if there are more ions per centimeter cube, if you compare over here, I'm pretty sure you can agree with me that there will be a stronger electric field over there, right? So the electric field over here is very strong, much stronger than what we have over here. And since the electric field is very strong, a small depletion region is formed because a very small region is enough to stop the charges from flowing. Unlike over here, if the depletion region was small over here, then maybe charges would further diffuse because the field is not strong enough. So you require a larger width. So you see, the more you dope, the more impurities you get, the smaller is the width of that. So the key takeaway of heavy doping is that it causes very thin depletion region, and that results from a very strong electric field over here. Alright, now let's reverse bias this thing. Well, when you reverse bias, you attach a positive to the N type and you put the negative to the P type. Notice as a result, you are increasing that electric field. Can you see that? Because this side was already positive over here, ions. So you made it more positive. This was already negative. You're making it more negative. So as a result, what happens is this electric field over here increases and the depletion region widens. That causes a minority carriers to go from here to here. But if you apply the same reverse bias over here, you apply that exact same reverse voltage over here, the electric field gets way stronger. The electric field strength becomes incredibly strong in this region. The reason for that is, you can think of it like this. You see, if you think about the voltage as the difference in height between 2 points, like you have a low height over here and you have a higher height over here, if the difference in the height is over a large span like this, as you can see, then notice that the slope that connects them is not much. It's not much a steep slope. On the other hand, if you were to take this same voltage difference, same height difference, but if you were to make sure that it's not on a large span, it's on a very tiny span, then you can see as you make it tinier and tinier and you connect them, notice that the slope increases. Can you see that? It is now more sloping than before. Electric field is that slope. All right. So the tinier is the depletion width, and even for the same voltage, the tinier the depletion width, more is the electric field in this region. So as a result, even for a very modest reverse voltage that you provide, like, I don't know, maybe 2 or 3 volts, the electric field over here skyrockets. Electric field over here is still pretty much modest. All right, so as a result, minority charge carriers start flowing in the opposite direction. The holes over here start getting swept across. Electrons over here start getting swept across like this. That causes a small current, a tiny current from P to N. And pretty much the same current flows over here as well. We've seen that before. It's independent of the voltage. Same current flows over here. All right, now let's see what happens when you turn up the voltage. We've seen this before. We're doing it one more time. If we turn up that voltage, let's say we go all the way to something like, I don't know, 10 volts or maybe even 15 volts. What happens? Well, we'll have to zoom in a little bit again to see what happens. Remember, right at this depletion region, we don't have any free electrons, but we have all these covalently bonded electrons. They're there. We don't show them. And now, due to this strong electric field that's generated when you go to, I don't know, 15 volts or something, these free electrons, maybe this is one free electron, this glowing thing, when this free electron gets a huge acceleration, it can hit one of these covalently bonded electrons, and it can knock it loose. So it can knock it loose, and due to this impact, you can see more charge carriers are being created. We call this usually as the impact ionization, because due to impact, you're freeing that electron. Whatever. Due to this impact, you get more and more charge carriers, and these electrons can further go and impact more, and that's where the whole avalanche effect takes place. We've talked about this before. But what happens over here in a heavily doped diode? Well, over here, if we zoom in, the structure is pretty much the same, but the chances of a free electron knocking any of these electrons loose is very tiny. And the reason it's so tiny is because the depletion region is very tiny, and so, the probability is just very small. However, something totally different happens. Because the electric field over here is so incredibly strong, that electric field itself is able to pull these electrons out of the covalent bond. So it's the electric field that removes the electrons from their covalent bonds, even at low voltages, you see, because of strong electric field. And we'll talk a little bit about why this happens later on, but that increases the minority charge carriers over here, and now the whole thing can undergo breakdown. So you see the breakdown that happens over here, a large current that starts flowing over here, is not because of impact. You see, over here it was due to the impact and the avalanche effect. This is not impact. This is happening because of the strong electric field. It's the electric field that's pulling out all these electrons, and as a result, a huge current starts flowing. This mechanism is called the Zener mechanism. And this phenomena, or this breakdown, is called the Zener breakdown. So if you look at the VI characteristics of under reverse bias for a conventional diode, then we've seen that pretty much a very constant current flows, very tiny, and here is where this avalanche effect is coming into picture, and a huge current is flowing. We call this as the breakdown voltage, the reverse breakdown voltage. But if we were to plot the same curve for a heavily doped diode, a Zener diode, then we would expect this same breakdown to happen at a much lower voltage due to the Zener mechanism, right? So this is what we would expect to happen for a heavily doped diode. So the difference is that this happens at a much lower voltage. So let me write that down. This happens at a much lower voltage. We call this as VZ, the Zener breakdown voltage. And because there is no impact happening over here, there's hardly any heating taking place. You see, that's the major problem with the avalanche breakdown. It can heat up the entire diode, and as a result, diode could melt. But over here, that won't happen because there are no impacts happening. The electrons are they're not being knocked off, they're just being pulled by the field. And so this current does not produce a lot of heat. All right, that's pretty much it. We could stop over here, but let's go a little bit deeper and understand the mechanism over here. There's a very cool phenomenon. Let's try to understand that. Let me get rid of this graph for a while. Here's the question. Why can't the electric field over here, pull out electrons from the covalent bond? Why can't they do that? Why only it happens over here? To answer that question, we need to really understand what these electrons feel. So we can think of these covalently bonded electrons as, you can think of a mountain over here. Imagine you have some kind of a weird mountain like this. It's a downhill. And you can imagine that this ball represents the electron, is sitting right over here. Okay, so this covalently bonded electron is like this ball. You see, the electric field is actually trying to pull these electrons. They want to accelerate the electrons towards the right, but they can't. Just like how gravity is trying to pull it down, you see there's a slope over here. Gravity is trying to pull it down, but they can't because of this barrier. So if this ball wants to fall down, it first has to, go all the way uphill. It has to overcome that barrier and then fall down. And that's the reason why these electrons are not able to accelerate. And that's why you need some impact. So these free electrons, they come and impact. It's pretty much like, some energy is given to this ball. So if some another ball comes and impacts this, that energy is enough to take it over that hill, and then they can accelerate down, right? So that's why impact ionization causes free charge carriers and acceleration and everything. What happens over here? Well, the difference over here is the depletion width is very tiny. So the whole mountain, they still have this, maybe the same potential difference, but the whole mountain becomes thinner, or not thinner, becomes narrower. So the mountain becomes something like this. All right, now imagine you have a mountain like this, and you have that same ball over here. You might expect, okay, how does that help? Well, now what's going to happen is that the ball will just go straight through and then accelerate down. You get that? This is a quantum effect. This cannot be explained by using Newton's laws or whatever, because classically you might think that it has to go uphill and then come down, but quantum mechanically it turns out it can just go straight through. This effect is called tunneling. All right, it's a quantum effect. It's called tunneling, where the electron is able to overcome the barrier and just go straight through, even though it doesn't have the energy to do that. And that's why these electrons are literally tunneling through this barrier and becoming free, and that's how they're accelerating. So the reason, we'll not talk about why this happens. It turns out it's got to do something with the dual nature of electrons and its probabilities or whatever, but we'll not talk too much about that. But this phenomena, why doesn't it happen over here? Well, it turns out that this tunneling really depends on two things. It depends on, one, how sloping this is. More the slope, more the chances of tunneling, and more importantly, how thin this is. The thinner it is, more the chances of tunneling. So over here, this diode is getting everything right for tunneling, and that's why the Zener breakdown, the tunneling effect is kicking in over there. But over here, the problem is that this mountain is very wide, and once it becomes wide enough, the tunneling probability almost goes to zero, and that's why you don't see any tunneling effect over here, but you see the tunneling effect over there. So the Zener mechanism is truly due to the quantum mechanical tunneling.